This is our final video for General Chemistry 1. We'll look at problem solving related to the concepts in Chapter 12 on intermolecular forces. As we saw, intermolecular forces arise from the attraction between molecules or between ions and molecules. And as such, these forces are significantly weaker compared to ionic bonding, covalent bonding, and metallic bonding, because we're looking at partial charges when we're looking at molecules, as we're looking at partial charges due to dipoles, or with ions and molecules, again, we're looking at partial charges or induced partial charges on the molecules. So the charges are smaller, but as well, the distances between the charges are larger. We're looking at van der Waals radii as opposed to ionic radii or covalent radii or metallic radii, which are much smaller. So the larger distances and smaller charges mean the forces are weaker. Here's a table that lists the common intermolecular forces. They're listed from strongest at the top to weakest at the bottom. The strongest forces are generally associated with ion dipole systems. This is followed by hydrogen bonding forces. Next are dipole-dipole forces, then in ion-induced dipole forces. Next are dipole-induced dipole, and the weakest are induced dipole forces, or what are called dispersion forces or London forces. For our first problem, let's look at a series of molecules that some of which we've looked at earlier. We're going to look at the strongest intermolecular force within pure samples of the following compounds. That could be gaseous or liquid forms of these compounds. And some of these compounds we've looked at with respect to their Lewis dot structures, with respect to their VSEPR electron group arrangements and molecular shapes. We've done orbital hybridizations with them, and we've developed valence bond descriptions for their covalent bonding interactions. So now let's take some of this information, see if we can identify from the shapes what dipoles might be contributing or other intermolecular forces. We'll start off with oxygen difluoride. We saw this molecule early on, and it has a V-shaped structure. Oxygen has a tetrahedral electron group, and there are two lone pairs. In this case, fluorine is more electronegative, so the fluorine end of the molecule is negatively charged, and the oxygen end is positively charged. Fluorines point downward, and so the fluorine end is negative. As we go to think about the strongest intermolecular force, we can first look at the strongest force, ion dipole, and of course there are no ions here. It's a pure sample of a covalent compound. There's no hydrogen bonding because there are no hydrogen atoms. The next strongest force is the dipole force, and we see in this case the molecule does have a dipole moment. Therefore, the strongest intermolecular force that occurs in pure oxygen difluoride is the dipole-dipole force. There will be contributions, of course, from other weaker forces, which will involve temporary dipoles and dispersion forces. Our next molecule is carbonic acid. When we looked at carbonic acid, there's actually two different central atom groups, but let's look at the carbon central atom. And the molecular shape about the carbon, of course, is a trigonal planar structure. It's a flat molecule. It's trigonal planar. There are no lone pairs, and there's 3 electron groups. In this case, of course, we have the oxygens with the hydrogens on them, but then we have another oxygen without any hydrogens, and so there'll be a dipole associated with this structure. There'll also be smaller dipoles associated with the oxygen-hydrogen bonds on the other end. So there are dipolar forces here, clearly, but there are no ions. So in a pure sample of this material, there are not pure liquid samples, but in a gaseous sample of carbonic acid, two molecules of carbonic acid that interact will have no ions nearby, but they will have hydrogen bonding forces. So we have hydrogen bonding as the strongest intermolecular force. There's also going to be dipole-dipole forces. Now, carbonic acid is generally found in water, and when it's found in water, carbonic acid is a weak acid. It dissociates and forms an ion. And in that case, the strongest force will then be an ion dipole force between the ionic carbonic acid structures, the deprotonated, the conjugate base forms, and the water. But in pure carbonic acid, the strongest intermolecular force would be hydrogen bonding. Next up is nitroxyl. When we look to the shape of nitroxyl, we see that it is a V-shaped molecule. The molecule will have a dipole moment on this. The oxygen end will be negative, and the other end will be positive. But we notice there are no ions around. The existence, though, of the nitrogen-hydrogen bond introduces a stronger force than dipolar force, and that is the hydrogen bonding force. So the molecule does have a dipole moment, and there are dipole-dipole forces, but this also has a nitrogen-hydrogen bond, so its strongest intermolecular force is going to be hydrogen bonding. Next molecule we'll look at is carbon disulfide. We've not looked at this yet with respect to its shape or its bonding. But if you want to take a moment and stop the video, you can sketch out the Lewis dot structure and the VSEPR shape for carbon disulfide. Now, if you do that, you should end up with a Lewis dot structure that looks thusly. The central carbon atom has a double bond to each of the sulfurs. And this molecule then is linear because there are two electron groups, and each side has the same carbon-sulfur bond, so the two carbon-sulfur dipoles, which actually are extremely small as well, we cancel. So this molecule is linear, but it has no dipole moment. There's no dipole moment, there are no ions around, there's no hydrogen bonding interactions, therefore this molecule will only have London dispersion forces. That will be the strongest force in carbon disulfide. Our next molecule is iodine trifluoride. We looked at this with respect to all of its structural properties and bonding properties earlier, and we note that this is a T-shaped molecule. If you look at this T-shaped molecule, you can deduce whether this has a dipole or not. So there are three fluorines. Two of them are axial. One is equatorial, in the same plane as the lone pairs. Two fluorines that are axial, while they may not be truly collinear, they do tend to counterbalance one another with respect to their dipole moment. But the iodine with the equatorial fluorine will have a dipole associated with that, and it's not counterbalanced by anything on the other side. The fluorine side will be negative. The iodine side will be positive. It has a lower electronegativity. This molecule has a dipole moment. There are no ions in this system, and there are no hydrogen atoms, so the dipolar force is the strongest. So in this case, then we identify the strongest intermolecular force as dipole-dipole. Next, we'll look at phase changes. We looked at the quantitative aspects, and we identified within a given phase, so within the gaseous phase, or within the liquid phase, or within the solid phase, if we have a temperature change, then heat flow occurs. And anytime heat flow occurs, there will be a change in temperature. And we can identify the heat associated with this as Q is equal to m Cp bar delta T. At the phase boundaries, so when we go from solid to liquid or from liquid to gas, we see that heat flows during the phase change without a temperature change. Therefore, the heat equation is given by m times the standard enthalpy for the phase change that you're considering. So, based on those equations, let's calculate the heat flow when a 25-gram piece of ice at 248 Kelvin is heated to 298 Kelvin. We'll consider the ice or the water sample as the system. So we'll look at Q with respect to the water. And we know that there are 3 steps to this process. First, we heat the solid water from 248 Kelvin to the freezing point of water, which is 273 Kelvin. Once we've reached the freezing point, then we begin melting the water. So at 273 Kelvin, we convert from solid to liquid. Then we heat the liquid water from 273 Kelvin up to 298 Kelvin. Those are our individual steps. The overall heat flow is going to be the sum of the heat flows of each of these steps. And we can see that the first step then, we can identify Q as m Cp bar delta T. We need to make sure to use the correct specific heat capacity. In this case, it will be for solid water, which is significantly lower than that for the liquid water. For step number 2, we're looking at a phase change, so Q will equal m times the standard enthalpy for that process. And then step 3, the heat flow is the mass times specific heat times delta T, in this case using the specific heat capacity for water as a liquid. Here we are with step 1 now. We have Q is equal to m Cp bar delta T. Cp bar is 2 joules per gram Kelvin. M is 25 grams. Delta T is 25 Kelvin. Therefore, Q calculates out to be plus 1,250 joules. Step 2, now we're looking at Q is equal to m times standard enthalpy for fusion. In this case, we're converting water solid to water liquid. So the standard enthalpy of fusion is equal to 334 joule per gram. We have 25 grams. Therefore, the heat flow calculates out to be 8,350 joules, and this is a positive number again. Finally, step 3, Q is equal to m Cp bar delta T. Here, though, we need the specific heat capacity for liquid water, which is 4.18 joules per gram Kelvin, more than twice that for the solid water. M is again 25 grams, and delta T is again 25 Kelvin. So Q is equal to plus 2,613 joules. So if we're going to calculate the heat flow, we need the total heat flow for the entire process. That's the sum of the heats for all the individual steps. In this case, we add those together, and we end up with 12,000 joules or 12 kilojoules of heat. The value is positive as the heat flows into our system. This is an endothermic process. Next, we'll look at the liquid-gas equilibrium, which is what we call vapor pressure. If we allow a liquid to equilibrate with its pure gaseous state, we see that vapor is created above the liquid, and this is a temperature-dependent equilibrium. As the temperature increases, the pressure of the gas increases. So the vapor pressure goes up. And an equation that approximately describes this is called the Clausius-Clapeyron equation. There are experimental data, but this gives good estimates of what the values are, where natural log of the pressure is equal to minus the enthalpy of vaporization divided by the gas constant in energy units times 1 over T plus a constant of integration. If we do a 2-point version of this, we have an approximate expression here where natural log of P2 over P1 is minus standard enthalpy of vaporization over R times 1 over T2 minus 1 over T1, where T2 and P2 represent the temperature, vapor pressure pair, and T1, P1 represent a different temperature, vapor pressure pair. It's important to note here that the enthalpy of vaporization is not a constant as a function of temperature. Delta H of vaporization varies with temperature. So this is an approximation, and you only have to use this as an approximation. If you wanted to do a more full treatment, you would have to use integrals to solve this, and that's beyond the scope of this class. So let's calculate a vapor pressure for water at 338 Kelvin if the enthalpy of vaporization is treated as a constant at 40.7 kilojoules per mole. Enthalpy of vaporization, of course, that's going to be an endothermic process because you're going from a liquid to a gaseous state. So the equation we'll need is the 2-point equation. Ln P2 over P1 is minus delta H vaporization over R times 1 over T2 minus 1 over T1. But we need to have a standard value off of which we work, and that value can be the normal boiling point of water. Because we know at the normal boiling point of water, the vapor pressure is equal to 760 torr, the standard atmospheric pressure. So, using the normal boiling point of water and converting the enthalpy of vaporization to joules units, because we need to be careful. Delta H vaporization is in kilojoules per mole as given. R is in joules per Kelvin mole. So with this conversion, then we can plug in values. These are the values that we would plug in. Notice that the units all cancel because we're taking the log of a ratio of pressures. The pressures, of course, their units cancel. We take the log of a non-unit bearing quantity, so we have no units on the left. On the right-hand side, we're taking delta H of vaporization in kilojoules per mole. R is joule per Kelvin mole, and so all the units cancel out. We plug in our numbers, and we can solve for P2. So in this case, we've identified P1 is the normal boiling point. So at P1, that's 760 torr, and T1 would be 373 Kelvin, the normal boiling point of water. And if we go through and solve this, we get P2 is 196 torr. It turns out this number is slightly different than the experimentally observed value, the standardized table value, but it's very close. It's within a few percent, approximately a little better 5%. That concludes our videos for this course.